Hello, my name is Manuel Patchou. I am from the Communication Networks Institute of the Technical University Dortmund. Today I will be presenting you my work titled Hardware in the Simulation Loop Framework for Reproducible Testing of Rescue Robot Communications in Constrained Environments.
Network communications are omnipresent in robotics. Most robotic solutions heavily rely on communication networks. Therefore, the behavior of these solutions must be tested in various network conditions. This work proposes a framework concept to test robotic solutions in controlled network environments. I shall continue with an introduction of the concept, which is a framework template for hardware in the simulation loop platforms, especially simulated robotics using real network devices. The concept will be followed by a detailed example of its implementation into a simulation platform. Finally, the implemented platform is used to evaluate SCATES, a multilink-capable communication module we developed for rescue robotics applications. I will conclude the presentation with a summary and future work possibilities. The proposed concept has the following building blocks: a robotic and a network simulations, an artificial network degradation module, and the networking hardware. The robotic simulation must allow, among other things, to export the scenario in a commonly used format and to include a custom robot model. Advertising simulation data and controlling the robot from an external process must be possible as well. The network simulation must be provided with the scenario and the robot position to generate network metrics. The network metrics must be enforced in a transparent manner on the communication hardware used by the robot. The communication hardware must be connected over a link with good characteristics to both simulations. The concept is now complete. Scenario and position are used to generate network metrics, which shall modulate network transmission of control and payload data from and to the robot. Let's now have a look at the concept implementation we carried out. We will be starting with the robotic simulation. For the robotic simulation, we used the virtual DARPA Subterranean challenge simulation, which is built on Ignition Gazebo. Robot models can be imported and scenarios can be defined as well. Now the robotic simulation is set. Next, we must define the network simulation component. For the network simulation, we used the Altair WinProp tool to generate signal strength, heat maps, and technology-specific connectivity maps of the simulation scenario. The network simulation being set, we move on to the artificial network degradation. For traffic shaping, we use NetM. NetM is a network emulator integrated into Linux kernel. It influences the transmission of data packets based on policies defined by network metrics. The metrics produced by the network simulation are transformed in NetM policies, which then control the transmission of data originating from the robot simulation. With the artificial network degradation being set, our implementation is now complete. The build platform can be used to conduct robotic simulations while varying the network conditions to investigate the robot's behavior and performance. It can also be used to test and verify the behavior of network devices which were designed to provide robot connectivity. This is what we shall be doing next. We will now conduct an experiment to verify the behavior of SCATES. SCATES is a module developed to provide more robust robot connectivity by using multiple radio access technologies simultaneously and aggregating them in a so-called multilink. The module can be extended with network cards and used with common or even proprietary IP-based communication technologies. The goal of the experiment is to ensure that traffic is shared among the available radio access technologies of the module. Here is an illustration of the simulation scenario with simulation parameters. The scenario is a tunnel circuit with an LTE base station and Wi-Fi access point deployed at the tunnel entrance. A Wi-Fi repeater shall be deployed by the robot during its exploration of the tunnel to expand the Wi-Fi's range. The imported model of the racer robot we used was equipped with camera sensors to transmit footage of the tunnel exploration. The hardware setup shall now be detailed. The simulation computer and the control station are both hosted on the same computer. The first skates module is used by the robot in the simulation. The second one is used at the control station to communicate with the robot. Both modules are linked to the simulation computer by Ethernet cables, while the Wi-Fi and the LTE links between the skates modules are simulated over two separated wired connections. The video stream of robot's exploration is forwarded over the simulated air interface by the skates module, while the control input sent by the robot operator travels the same path but in opposite directions. Therefore, a video transmitter, a video receiver, and a robot control node are run on the simulation computer. And the skates module embedded on the robot has the network simulation and the artificial network degradation running. The skates module at the control station handles the multilink traffic and logs it to allow monitoring and evaluation.
Our setup is now complete. Here is an overview of the platform implementation. We shall now discuss the results of the investigation conducted with the implemented platform. Here we can see the raytracing results generated by Reprod for the signal strength of different communication technologies in the provided tunnel scenario. The locations of the access points are easily noticeable. The LTE base station, for example, is located before the tunnel entrance in the staging area, while the Wi-Fi access point is located at the first cross just after the tunnel entrance, and the Wi-Fi repeater is deployed in the lower right corner of the tunnel. The corresponding throughput maximum was recorded during a test run of the robot through the tunnel. The LTE throughput is high near the tunnel entrance and even after the upper right corner of the tunnel. This is mostly due to the line of sight conditions and the lower frequency band which was used. The LTE throughput reaches its lowest at the lower right corner of the tunnel due to the combined effects of the obstacles and the distance. A similar pattern is observed for the Wi-Fi throughput, which is however much more affected by obstacles due to the higher frequency range it operates in. The deployment of the repeater brings some relief in the lower right corner and raises the throughput back to line of sight levels. Here is a plot of the traffic measured on the network interfaces of the skates module at the control station. That is the skates module receiving the video on the multilink. The network constraints, namely the dashed lines which represent the maximal achievable value of the throughput on each link, are plotted as well. The total traffic is also visible. The effects of the obstacles are noticeable as the Wi-Fi declines, which is followed just after by LTE. The enhancement brought by the repeater deployment can be confirmed too. First, it can be seen that the throughput upper bounds are not exceeded. The network constraints are respected. Furthermore, the overall traffic is much higher than each one of both links, as the transmission occurs on both communication technologies, truthfully following the multilink approach.
Demo time. In this video we can see the simulation environment in the upper left and the received video stream in the upper right, while the network metrics are in the lower part. In the lower left we have the received traffic on the LTE and Wi-Fi interfaces, and in the lower right we have the traffic sent to the control station. At the beginning we have good throughput, and we have a good throughput that changes as soon as the robot takes the first turn. And this causes the direct line of sight to the Wi-Fi base station to be lost, This has an immediate effect on the frame rate. As we can see, we get pictures less often in the stream, and after the Wi-Fi access point is deployed, the frame rate goes back up.
Time to sum it up. So we presented a concept for simulating robots in under-provisioned network environments, and which can also be used to evaluate communication hardware. An implementation of the concept was provided as well, supporting flexible scenario and robot definitions and reproducible network environments. In the future, we plan to extend this work by upgrading the network simulation module with online simulation and computation capabilities of network metrics. This would be a good basis for providing native support of dynamic network configuration. I am now at the end of my presentation. Thank you very much for your attention, and I am now open to your questions.